Okay. Morning, everybody. Oh, no. Afternoon, sorry, not morning. Nice to see you all. My name's Rob, first of all. So I'm a particle physicist, technically, not an astrophysicist. But a lot of my work, my research work, involves things that happen in space and involves a field, please come in, called cosmology. So cosmology, is about studying the universe as a whole on the very largest scales. So although a lot of my work focuses on very tiny things, particle physics, things smaller than an atom, I sort of apply this to things that are much, much larger, at the scale of the entire universe. But today I'm not talking so much about particle physics or cosmology. I want to talk to you about these fascinating objects that exist in the cosmos called pulsars. So in order to learn more about these, we're going to take a bit of a journey from formation, the objects that form pulsars. So we're going to talk about stars. And we're going to talk about some of the underlying physics that is responsible for the properties these very bizarre objects have. So you see I have a few nice toys at the front, so these will come into play a little bit later. But for now, let's just take a look at the rough outline we're going to discuss. So first of all, we're going to talk about the history behind the discovery of pulsars, because actually the history of how these things were first detected and how we first established what they actually are, because of course there are no pulsars even remotely near to the Earth. We certainly have never visited near to one. We have never been to a pulsar. It's in fact very hard to actually see them, like we can see stars in the night sky, regular stars, because pulsars don't really shine with visible light. The way we see them is slightly different. So the detection and their history of their discovery is very interesting. Then we're going to talk about neutron stars. So a pulsar and a neutron star, these are essentially the same object, but a pulsar is a sort of slightly special version of a neutron star. We'll discuss all of these terms. Don't worry if they're not familiar. And then in answering where pulsars come from, we're going to talk in a little bit more detail about the life cycle of a star. And moving on from that, we'll talk about the properties pulsars have, where these properties come from. So they have some very strange behavior that we will discuss. We probably won't talk about pulsars as tools for new discovery, just because I think we might not have time. And I want to leave lots of time for questions as well. So as we're going through, if you do have questions that come up while I'm talking, I'm very happy to take them as and when they come up, as long as we can get through some of the content. I know, Henry, I'm sure you've got plenty of questions, so we might have to save some till the end. But let's get started, okay? So the story starts about 60 years ago, in the late 1960s, with a young physics PhD student called Jocelyn, at the time just Jocelyn Bell, later Jocelyn Bell Burnell when she married. And a couple of miles southwest of Cambridge, she notices a string of radio pulses, exactly 1 1/3 seconds apart. So this is unusual because although radio signals coming from space are not completely bizarre, having them appear so regularly, exactly 1 1/3 second apart, is quite a novel thing. So this is a pretty confusing observation, and just to show you some of the glamour of radio astronomy, this is what's left of the radio telescope that was used for these initial observations. It actually doesn't really look that much different today than it did at the time. They have to use flocks of sheep to mow the grass because you can't get mowers between the radio poles that detect the signals. So, yeah, this doesn't look like sophisticated equipment, but actually this is still pretty much how the observatory looks now, this part of the observatory. Okay. So when these pulses are first detected, initially, so here is, first of all, is the actual data sheet that she first recorded these pulses of radio waves coming from space on. When these are first detected, they are sort of jokingly nicknamed LGMs, or little green men, because, again, the regularity of these pulses, exactly 1 1/3 second apart, is such a bizarre and seemingly alien phenomenon that there's no natural source known that we can attribute it to. So although it wasn't seriously thought that these things were actually extraterrestrial, of course, it's not completely ridiculous that they could have been, and there was no better explanation at the time. So this is a somewhat joking name given by Jocelyn Bell at the time and her PhD supervisor, Anthony Hewish. So the signal that's recorded up here in the top left is a signal of radio pulses. So this is dated 1967. These little peaks here, these little bumps, are pulses of radio waves that are detected at this the Mullard Radio Astronomy Observatory just outside of Cambridge. Okay. Now, of course, these signals are not actually from aliens. These are not actually little green men. But then the question is, well, where are they coming from? What are these signals? So, prior to the detection of these radio signals, other scientists, so in particular Walter Bade and Fritz Zwicky, had posited the existence of an exotic end state of a star. So, of course, our sun is one example of a star, but there are billions and billions of stars in our galaxy, even more galaxies than there are stars, so countless numbers of stars in the universe as a whole. And they had hypothesized that after a star dies, after a very large star undergoes this explosive death we call a supernova, it can leave behind a sort of cold, dead core that we call a neutron star. So we've never, up to this point, when they make these predictions in the 1930s, we've never seen a neutron star. We've never looked at one through a telescope. We've never detected any signals of one, but purely based on their theoretical calculations. So, you know, the maths that they know, the physical laws that they know, they can put two and two together, and they make a prediction that these objects might be possible. They might exist in the cosmos. And here's a sort of an artist's depiction of what a neutron star might look like if you were to get up close to one. And the thing I want to point out that we will come back to is this super strong magnetic field. These lines here represent the fact that a neutron star is an extremely powerful magnet, which is responsible for some of its properties. A few years later, so now in the 1960s, Lodewijk Volcher proposes that these neutron stars, if they existed, remember we haven't seen them yet, this is a few years before Jocelyn Bell discovers these pulsed signals, they propose that if they exist, they would have a very strong magnetic field. Okay? Why does that matter? We'll come back to why the magnetic field is so important in linking these seemingly disconnected things. We've got the theoretical prediction that maybe something called a neutron star might exist, based on their maths, based on their calculations, all done theoretically. And then we've got this signal, this radio pulse signal that's discovered some years later. So at the moment, these two things seem completely disconnected. But part of the link in this chain that connects the two ideas is this fact that the neutron star, if it did exist, should have a super strong magnetic field. So that's discovered by this chap here. A couple of years later, Franco Pacino, he establishes that not only does a neutron star have a very strong magnetic field, but additionally, it would spin very quickly. So it rotates like the Earth rotates, but much, much, much faster. And the action of this spinning magnetic field produces jets of radiation, jets of, for example, radio waves. Okay? So there's a prediction that these neutron stars, if they exist, have a strong magnetic field, they spin very fast, and as a result, they produce radio waves. So we can start to see here where the link, the theory of neutron stars might be able to produce radio waves if they exist, and the observation, the fact that we see these mysterious radio pulses coming from the sky. That's the link between these two. So a couple of years later, just 1 year after Jocelyn Bell observes these radio pulses, Richard Lovelace and his collaborators make an observation of another source of radio pulses, but this time in the Crab Nebula. So this is actually a picture of the region of the Crab Nebula, which has what we now know as a pulsar within it. here is the full view of the Crab Nebula, which is it's a very sort of famous photo in astronomy that you might have seen before. The pulsar that they observe, so they get a similar sort of set of readings, radio flashes coming in towards them. And the flashes they get are extremely rapid. So the flashes they get are about 30 every single second. So, really, really high frequency flashing. And all of the sort of theories we have to this point to try and explain what these flashes might be are impossible in producing that quick flashes. The only theory which allows for flashes to be that quick is the theory that these pulses are coming from a spinning neutron star. So this is sort of the final chink in the chain that allows us to link these observed radio flashes with the existence of a superfast spinning neutron star. Okay? So pulsars are neutron stars. This is established. And you can see, it's not just one person. There's the observation from Jocelyn Bell and her supervisor, Anthony Hewish. There's the theory that's done by the chaps I mentioned before, so Pacino and so on. But it all comes together for us to understand that these radio pulses are coming from this dead core, this super dense, super fast spinning dead core left behind when a star goes supernova. So science is, it's rarely just sort of one method and one experiment and one discovery, especially in astronomy where, in order for us to get information from the stars, from these extremely distant galaxies and these objects that are, sending us signals that our eyes can't actually see, not visible light, we have to bring in data and bring in theories from all over. So astronomy and astrophysics is extremely collaborative, okay, in bringing together lots of people and lots of different ideas. And I want to say as well, on the topic of Jocelyn Bell Burnell, so of course Jocelyn Bell observes these radio pulses. She discovers the radio pulses and sends the information to her supervisor and they chat about it together. And a few years later, her supervisor wins the Nobel Prize for advances in radio astronomy and Jocelyn Burnell does not. So it's a real actual injustice in physics that's recognized today as not quite right. But she did win a very, very large physics prize, so a multi-million-pound physics prize, so you can never say that doing physics doesn't pay. And then she donated it all to fund research scholarships for female and other underrepresented groups in physics. So she's an extremely impressive woman, an extremely good scientist as well. Okay, so pulsars are neutron stars, and in this case, theory is leading discovery. The idea that neutron stars might exist very much precedes the detection of, real evidence that they are there. Okay, so the theory that they might exist comes out in the 1930s, but then the detection of these radio flashes is not until the 1960s, so much later on. Okay. Did anyone have any questions just on what we've spoken about so far? Yep. Is the sun big enough to turn into a neutron star when it goes into supernova? That's a very good question. So in fact, our sun will not even go supernova. Our sun is not quite large enough. Only the very largest stars will go supernova. That's a very good question. So our sun will turn into something else. So there's a whole class of what are called stellar remnants. It's left over from when a star dies. Our sun will form what's called a white dwarf star, which is similar to a neutron star in some ways in that it's also very dense. It doesn't make new heat. It just sort of stays hot and cools down over billions and billions of years. But it's not quite as dense as a neutron star, and it doesn't have as many interesting properties. Still very cool. Neutron star is another possible outcome that happens if the star is a bit bigger than our sun. And then the sort of ultimate, big daddy of stellar remnants is a black hole, which happens if you have a really very enormous star. I am talking more about black holes at the end of May. I'll give you the dates of that later on, but yeah, different kinds of stellar remnants. Any other questions from anyone else? Yeah?
So after billions and millions and eternity, for example, could it turn into colder planets? So could it turn into a colder planet? Or will it just cool down for eternity and it will just stay cool down, or will it turn into a planet?
That's a brilliant question. So it won't turn into a planet. The planet is a different kind of object. You know, planet is something that's made up of rocks and dust, obviously condensed down into something solid like our Earth, like our planet. But certainly the cooling part, you're absolutely right, because it doesn't make new heat, and because the universe, you know, the space surrounding it is extremely cold, it's going to emit heat radiation, and it's going to cool down, but it takes billions of years for them to cool. At least, you know, for white dwarfs and neutron stars, these are actually one of the ways that we can constrain how old the universe is, because we have, you know, theories about the cooling of white dwarf stars and neutron stars, and the theories are that for them to get down to a certain temperature, it would actually take longer than the age of the universe. So there aren't yet any very super cold stars. But there's a name we give to what's a white dwarf star. So this is the kind of star that our sun will become. When our sun dies in about 5 billion years' time, that will turn into a white dwarf, which is very hot, and then after billions and billions of years, it will cool down and it will turn into what we call a black dwarf, because it will be so cold it will no longer be glowing like a white dwarf is, but it will become cold and you could perhaps stand on the surface of it, although the gravity might crush you. Okay? Very good. Yeah, did you have a question?
I was just saying that it's linking to that person's question.
Uh-huh.
But the sun does have like a rocky surface, doesn't it?
No, the sun doesn't. So the sun is made up mostly of two things. It's made up of hydrogen and it's made up of helium. And these things inside of the sun are, because the sun is so hot, and we'll talk about why the sun is hot and how it stays hot in a minute, but because the sun is so hot, these gases of hydrogen and helium, they're sort of pulled apart a little bit. So they turn into a different kind of matter. So you know you've got the three states of matter. You've got solids, and you've got liquids, and you've got gases. So the sun is actually not quite either of these. It's none of those three. It's a fourth one that we call, does anyone know what the fourth state of matter is? Yes? A plasma. Yeah, the fourth one is what we call a plasma. So this is just a very kind of super, super hot gas, where the gas molecules have kind of come apart a little bit. And it behaves very complicated, in a very complicated way, in a very dynamic way, but it's not solid and rocky. It's sort of like, you know, it's gas, but it's a super hot gas, okay, held together by gravity. Does that make a bit of sense? Yeah? One more question, if anyone has one, and then we'll move on. No? Okay. All right, there'll be more chances later. Okay, so we're going to talk now a little bit about stars and about where stars come from. So I've mentioned back here I put up a picture of the Crab Nebula, and here's a more zoomed in picture of the Crab Nebula, complete with what we now know to be the pulsar at the center of it. But what is a nebula? So this is one of my favorite nebulae here. This is a picture of what's called the Carina Nebula. Like a phoenix from the ashes, stars are born from the corpses of their ancestors. So when a star dies, a very large star, and it undergoes this process of supernova, where it explodes and it spews its guts throughout the cosmos, mixtures of gas and dust and so on. From this collection of gas and dust, new stars form. Okay, and we call these stellar nurseries, these star-forming regions within nebulae. Okay. So how does this work? Well, if you have a collection of gas, dust, and maybe some rocks, gravity is a force that attracts objects that have mass together. So gravity pulls things together. Anything that has mass will be pulled by gravity. So gravity sucks inwards this combination of gas, rocks, and dust. And in doing so, it sort of spirals in and it becomes more condensed. And it forms something we call a protostar, which is a sort of early, rebellious teenage phase of our sun. It behaves in a similar way to a regular star, except it's slightly more turbulent. It has an inspiraling disk of material falling in, and it often has jets of radiation shooting out of either end. But the important thing here is that as this material falls in towards the center and is squashed by gravity, it initiates a process called nuclear fusion. And this is what drives the energy within the star. This is where the heat and the light of the star come from. Okay? So I want to talk a little bit more about what nuclear fusion is. So nuclear fusion as a process is where smaller nuclei, so of course you have an atom. An atom has sort of two major parts to it. It has a nucleus at the center, and then it has electrons spiraling around it, which are smaller, negatively charged particles. You've seen this sort of classic picture of an atom, right, with thing in the middle and then a sort of circle thing spiraling around it. So the nucleus is the thing in the middle. And the very, very high temperatures and very high pressures within a star are able to squash these different nuclei together and crush them to make a new nucleus. So you can see here, like a little jigsaw puzzle, if you fit these two together, these two what are called deuterium nuclei together, they form a helium nucleus. And in doing so, a large amount of energy is released. Okay? So this particular reaction here, combining two deuterium nuclei into a single helium nucleus, is the principal reaction that happens within our own sun to generate the heat and the light that our sun produces. Okay? But why does it generate energy? Well, we're going to talk about Einstein's extremely famous formula, E = mc squared. Now, the little triangle symbol I've written here is just to remind me that this is a change in mass. This is the mass lost, as I will explain. So if I take these two deuterium nuclei, okay, and if I add up their masses, I get this number here. Now, don't worry so much about the 10 to the power of minus 27. That's just telling me that the 6.68 before it has 27 zeros, 0.000000, and so on and so on. So very tiny mass. Focus just on the 6.68. So this is the mass of the two deuterium nuclei. Now, the mass of the helium nucleus, remember, the helium nucleus has just been made by squashing these two together. You would expect, right, if you're making a cake and you put 500 grams of sugar in the bowl, and then you add another 300 grams of sugar, how much would you have? Shout it out. 800 grams of sugar. Yeah, right. Mass is conserved. When you add up the masses, you have the sum of the masses at the end. Okay? But what we're showing here is that actually what you have at the end when you squash together these two nuclei is not quite the same as what you started out with. We first had 6.68. I've now got 6.64. So I've lost 0.04 of mass. And that is what the delta M, the change in mass in Einstein's formula, represents. The mass lost when you squash these nuclei together, we multiply by c squared. Now, c is the speed of light, which is a very big number, 300 million meters per second. You square this so it gets even bigger. It becomes a 9 with 16 zeros at the end. And you multiply them by the very tiny mass we have here, which I'm just showing you. That's the mass that's lost when we squash these two together to make the helium. And when you do that calculation, you get this number here. Again, don't worry too much about this number. But to put that into perspective, if you had 1 gram, so 1 single gram of these deuterium nuclei, okay, and you squash them together, you would make 540 billion joules of energy. And again, to put that in perspective, that's how much coal you would have to burn to get that same amount of energy. You would have to burn 18,500 kilograms of coal to get the same amount of energy as 1 single gram of deuterium being fused together. That's the power of nuclear fusion. Okay? When you start changing elements at the nuclear scale, you release huge amounts of energy, which is why the sun is so hot, okay? Because it's constantly undergoing this process of nuclear fusion in its core. This is also why, if humanity could unlock the power of nuclear fusion, what we call cold fusion, it would absolutely solve all of our energy needs overnight. Because what's the ingredient you use? The ingredient is deuterium. Now, deuterium, this is really just hydrogen. Okay, this is actually just a nucleus of hydrogen gas, but it has an extra particle in there called a neutron. So it's a variety of hydrogen. Okay, so we have this everywhere on Earth. Hydrogen itself is the most abundant element in the whole universe. And what's the outcome? The outcome is helium. Helium is completely safe. It's not radioactive. This is very different to the nuclear power, which works on nuclear fission that we have available today. So the result is helium gas, which is actually something we need and something the Earth is running out of, which is going to cause a lot of problems. And the thing we have to make it with is something that's extremely abundant. Okay? But it's a hard problem, getting it to work. So what does nuclear fusion do within the sun? So it makes the sun extremely hot, and it generates a thermal pressure that is pushing out. So if you heat something up, when you heat something up, it will tend to expand, right? If you've ever done that experiment at some point where you heat up a metal sphere and then you can't push it through the hoop, where you could when it was cold. Anyway, when things heat up, they expand. So they're pushing outwards with this thermal pressure. So we have two forces. You have the force of gravity that's trying to collapse the star inwards, to suck it inwards, and you have the force of this thermal pressure that is trying to explode the star outwards. And for most of a star's lifetime, these forces are in pretty much perfect balance, which is why our sun has approximately a fixed size. It doesn't suddenly double in size or suddenly halve in size. It's in a state of equilibrium. And we call this very nice, well-behaved stage that our sun is at the main sequence phase. Okay, this is like the middle age of a star's life cycle. Now, interesting things happen when one of these forces gets the upper hand. So we have the force of gravity compressing inwards. We have the thermal pressure trying to explode outwards. When one changes, the whole structure of the star changes. So this is a little bit of a busy diagram I've got here, but what happens is when the hydrogen, or the deuterium, I should say, that's being fused in the core of the star, when this starts to run out, the rate of nuclear fusion slows down. When the rate of nuclear fusion slows down, the star gets a little cooler. There's less thermal pressure. The thermal pressure weakens. And as a result, gravity now has the upper hand. Previously, they were balanced. When the hot pushing out force goes away, gravity pulls in and squashes the star a bit. Now, that squashing of the star actually leads to a rise in temperature inside of the star, because once the core contracts and the pressure rises, you start squashing together even bigger nuclei than before. So previously, we were squashing together hydrogen to make helium. Now you're squashing together helium to make heavier elements, okay? And as a result, the thermal pressure rises and the star expands. And so we're left with this new phase in a star's evolution that we call the red giant phase. So our sun, in about 5 billion years, will expand into a red giant, and then some number of billions of years after that will become a white dwarf star. And the difference in how these red giants behave to main sequence stars like our sun is quite stark. So they're, first of all, enormously larger, and I'll show you in a moment how the scale actually compares, and they're also quite a lot colder. So although you might think red hot means hotter, actually redder means cooler compared to yellow. A yellow star is hotter than a red star, and then a blue star is hotter than all of them combined. So there are blue stars actually. Blue supergiants are the hottest kind of star. So just to compare the size that our sun will have when it expands into a red giant, it won't be good news for us, unfortunately, but this won't happen for billions of years, so we don't have to worry too much. This is the sun as it is now. The blue line here is the orbit of the Earth around the Sun. And then these 3 different shaded regions here show 3 possibilities of how large the Sun might become when it expands to a red giant. The typical consensus is that it will probably get to about where the Earth is now. So the edge of the Sun will be on our front doorstep when the Sun turns into a red giant. It's going to grow by about 200 times. So it will be enormously larger and colder. Okay? The next step. So supernova. So this only happens to the very sort of largest stars, much larger than our own Sun. When the core of the star has become almost entirely made out of iron. So iron is the heaviest element that you can create by nuclear fusion within a star. Once the core becomes almost solid iron, you can't squash it anymore, you can't make it undergo fusion, and so it rapidly starts to cool down. Okay? And it's the same sort of story as the evolution from main sequence into red giant. When the core starts to cool down, gravity compresses it inwards, squashes it in, and that squashing it in suddenly causes the thermal pressure to rocket. The mechanism for this is a bit complicated, and it's also not entirely well understood because supernovae are quite rare. We don't see very many of them, and of course we never see any from up close, and we never see any of them from the inside out. So a lot of it again is all coming from theory, from calculations, computer simulations, and trying to match these with our observations of what we see. But it's thought that when the core collapses, it releases an enormous flux of these particles called neutrinos. And these neutrinos deposit a sort of catastrophic amount of energy into the outer layers of the star and cause the outer layers of the star to explode away from the collapsed core. So what we're left with from this collapse is this dead remnant, which in our case is a neutron star, in the case we're discussing, and surrounding it the sort of exploded guts of the previous star, okay? Forming the nebulae that we've seen before. So this is what we're left with. We're left with this so-called degenerate core of the star, which for our Sun will be a white dwarf, for larger suns will be a neutron star, and for even larger suns will be a black hole, surrounded by this cloud of gas and dust we call a nebula. So here, for example, is a section of the Veil Nebula. So the Veil Nebula, as it's called here, is one section of a larger structure that's called the Cygnus Loop Nebula. And the Cygnus Loop Nebula has within it a neutron star. Okay? So I want to talk now a little bit about the properties that pulsars have. So pulsars, just to remind you, are what we call these super fast spinning neutron stars. So we're going to go into the details of their composition, and we're going to talk about a handful of their other interesting properties. Okay? So first of all, what is a neutron star made of? Well, don't ask me too much about all of this complex stuff here, because actually my expertise is not in pulsars. I'm not quite sure what they mean by Swiss cheese, spaghetti phase up here. This is all about the exotic materials that happen that you have within a neutron star undergo very complicated phase transitions. But as the name suggests, a neutron star is made up almost entirely out of neutrons, which are a kind of subatomic particle that we get inside the nucleus of an atom. So the nucleus of an atom is made of 2 things. It's made of protons, that I've drawn in red here, and it's made up of neutrons, that I've drawn in white here. And spinning around the nucleus, you have electrons. Now, in the sort of hot plasma soup that makes up the inside of a star, these protons and electrons are all sort of floating around, crashing into each other. And when the pressure gets extremely large, when the core of the star collapses, it squashes together these electrons and these protons, and they turn into a particle called a neutron. In addition, they release something called a neutrino, and if you're interested in these particles, I'm giving a lecture on particle physics in the the second week of May, I think, but I'll give you the dates later. And this is what happens within the neutron star. The protons and the electrons squash together, they all turn into neutrons. And the The actual sort of cross-section of the star is a little bit more complicated. It has a crust. It has different phases of matter within it. These are all sort of exotic quantum phases of matter, superfluidic neutrons and all sorts of crazy things like that. So we're not going to go into too much detail on that because, again, a lot of it is not understood, certainly not by me. Good. Density. So neutron stars are extremely dense. Typically, the radius of a neutron star is sort of in the sort of 20-kilometer range. Now, if you put that into perspective, if you take the center of where a neutron star would be as the Beecroft Gallery, where we are now, that 20 kilometers stretches roughly to Basildon, which might sound quite large, but you have to remember this is something that has a weight of about 10 to 25 times the weight of our whole sun. So this is something 10 times the mass of our sun squashed down into something that takes you just about to Basildon. Okay? So extremely dense, very, very dense, very, very tiny. How dense exactly? Well, I can give you a big number here. That's a 5 with 17 zeros at the end for how much matter you have in a given 1 meter cube of neutron star material. But in better terms, I will call this 15 million EPT, or elephants per teaspoon. So if you were to take 1 single teaspoon of neutron star material, this would have the weight of 15 million large African bull elephants. That's how much stuff is squashed into a tiny, tiny space within a neutron star. Enormously dense. And if any of you wanted to check my calculations, here are my calculations. So I've assumed a bull elephant is about this heavy. I've assumed a teaspoon is about this much. And then I've done the unit conversion. If any of you ever want to convert anything else into elephants per teaspoon. Okay? Spinning. So, neutron stars spin extremely quickly. And in order to understand why they spin extremely quickly, we need to talk about 2 principles in physics. We're going to talk about angular momentum, and we're going to talk about something called the moment of inertia. So, angular momentum, I describe it as how hard something is spinning. Okay? It's a property of things that spin that is conserved. It stays the same, okay, before and after a process occurs. Now, saying that it's conserved, that's not to say that a spinning object will always be spinning, but it is to say that if a spinning object stops spinning, it has to give a bit of its spinning to something else. So if you stop something spinning, you take away a bit of its spin. That's how I'm explaining angular momentum, okay? Moment of inertia, this is a measure of how distributed away from a rotation axis something is. So something that is very sort of flat and spread out has a high moment of inertia compared to something that is of maybe the same weight but much more condensed around an axis here. This would have a lower moment of inertia. Okay? So, I have an equation, but before you write down an equation, you should always understand what the equation means. So I'm going to demonstrate. Okay, so what I'm going to do is I'm going to give myself an initial spin. I'm going to give myself some angular momentum, and then I'm going to tuck my hands in. And I want you to observe what happens. I'm going to make sure I'm not going to hit anything. And I want you to try and explain why it happens. Why do we think it's happening? Okay. Okay, I'll do it one more time, or else my leg will cramp. Right. What happened? Did anyone notice? Yep, Henry?
So when you were spinning your outward, it was pretty more ready for you to be down. So it was slowing down the chair's rotation. Whereas when you
Okay.
as it had less push down on the outside, the chair spun around much more quickly than it did.
Right, it's a good theory. It's not quite what's going on here. It might have had some effect, you're right, but it's not quite what's going on here. What did you notice, though? What actually happened about when I tucked my arms in? What changed? What happened? Just at the sort of instant I tucked them in, what do you? I stopped spinning. Ah, well, does anyone have a different answer? Yeah? I sped up, actually, yeah. I stopped spinning afterwards, you're right, because obviously I can't spin forever, unfortunately. But yeah, when I first tucked them in, you noticed I zoomed around a little bit more. So why did that happen? Well, when I tucked my arms in, I went from this sort of distribution to this kind of distribution. I went from a high moment of inertia to a lower moment of inertia. And from my formula, the angular momentum, remember this is the same before and after. Whenever something is spinning, you can't get rid of angular momentum. You can transfer it, but you can't destroy it. So the moment of inertia got smaller when I tucked my hands in, but my angular momentum should have stayed the same. So I've got two sides of an equal sign. This side must always be the same as this side. This side doesn't change because my angular momentum is conserved. My moment of inertia gets smaller. Whoops. Press the wrong button. So my moment of inertia got smaller, and therefore my rotation speed had to increase in order to keep both sides of the equation balanced. Okay? So mathematically, that's why it happened. That's why my speed increased, because my angular momentum has to be conserved. I decreased my moment of inertia, and so I had to increase my rotation speed to compensate. Okay? So if you consider this for a star, you know, the core of a star is initially very big, but then when it collapses down to a neutron star, remember it's going from, you know, like the size of our sun to suddenly something that's about the size of here to Basildon. It's much smaller, much more condensed around its rotation axis. Moment of inertia decreases, and so the rotation speed massively increases. So this is why neutron stars, or pulsars, spin extremely rapidly, because they keep the angular momentum that they had before they collapsed, but because they've collapsed, they have to spin much more quickly to maintain it. Okay? Magnetic fields. So as we've said, pulsars have very strong magnetic fields. Now, the exact origin of where their magnetic field comes from is still not completely understood. These are super strong. You know, we're talking sort of trillions of times larger than the strength of the Earth's magnetic field. Really, really strong. So, you know, you can compare them to a little, well, an extremely large bar magnet here. You know, the magnetic field leaves the North Pole and it loops around back into the South Pole. Okay? And not only is this magnetic field there, but it's also rotating, because of course the neutron star is spinning. The neutron star has a magnetic field, so we have an extremely rapidly rotating magnetic field here. And I want to talk a little bit about what happens when you have a very fast moving or a very rapidly changing magnetic field. So, here I have a magnet here, and I have a loop of wire here. And I don't know if you can see here, I've got a little voltage meter, which is displaying the voltage through this loop of wire. So what happens is when I move... Oh, where is it? Oh, it's on the wrong side. That's why you can't see it. There we go. It's actually showing the current in the wire. When I move the magnet through the loop of wire, you can see that a current is induced in the loop of wire. Okay? So the lesson here is that a moving magnetic field, as we have from this bar magnet, creates an electric field. So the electric field is what pushes the current around in a loop of wire. Now what you might notice is that when the magnet is still, even if it's inside, there's no current. It's only when it moves you have the current. Okay? So only a moving magnetic field generates an electric field, generates an electrical current and an electric field. This is a phenomenon called electromagnetic induction, and this is, you know, by the way, the cornerstone of basically all of our power generation. Okay? Anything, whether it's coal or burning natural gas or wind turbines or geothermal power, it all ultimately comes down to spinning a magnet in a loop of wire and making a current. Okay? The only exception is solar power, which is generating a voltage in a different way. Okay? So, next item, what is light? So seemingly a bit of a step in a different direction. Can anyone tell me what is light? Who can give me a one-word? Yeah, you at the back, yeah. Ooh, very good. Okay, so you've thrown me off. That's brilliant. I like it. Okay, so light is very complicated. You're completely right. And you can think of it in terms of particles called photons. That's very good. There's a dual way of thinking about light. One side is to think of it as a particle, which is a photon, and there's another way of thinking about it too. Yeah? Another way of thinking about it is a wave. Now, you're both right. You're both completely correct. And this is the cornerstone of something called quantum mechanics. The fact that light is both a wave and a particle is what we call the wave-particle duality. So you're both right. But now I'm going to talk about it as a wave just for now, okay? But you're both completely correct. So I'm going to say light is a wave, although it is also a particle, okay? Now, but what is waving? You know, if you think of a water wave, you know, the surface of the water is what is waving. If you think of, you know, a Mexican wave, if you're in a crowd, the people's hands are what's waving up and down. What is waving for light? Can anyone answer that? What waves in light? What is it that's waving? It's a bit of a harder question. Henry, yeah?
Is it like the particles of like dark matter and antimatter pushing the light up?
Oh, wow. Not quite. That's an interesting thought, though. Dark matter and antimatter, really heavy stuff. Very good. It's not quite that in this case, okay? Any other theories? No? Okay. So light is the thing that's waving is the electromagnetic field, okay, which is a slightly more abstract idea than water waves or a Mexican wave, but it is nonetheless something physical that is around us all the time. So light is what we call an electromagnetic wave, meaning you know, a ray of light that travels, you know, bouncing all across this room right now has two components. Half of it is a magnetic field, half of it is an electrical field, okay? So why am I mentioning this? Well, we've just been talking about how a magnetic field moving generates an electrical field, generates an electrical current. And now we're saying that light itself is a mixture of electrical and magnetic fields. So this sort of helps us motivate one of the other interesting properties about pulsars, which is these extremely energetic beams of electromagnetic radiation that they have shooting out of their poles, okay? So given that light is an electromagnetic wave, and given that magnetic fields can make electric fields, we can start to understand the link between the highly spinning magnetic field of the pulsar and the jets of electromagnetic radiation they create as they spin. So these are, in this case, I've said this is an X-ray, but sometimes they are radio waves, as was the case in the first pulsar discovered. But these are all forms of electromagnetic wave, the same as light. Visible light that we see is an electromagnetic wave as well. So what happens if the Earth is in the path of one of these X-ray beams? It's not dangerous, don't worry. It's very, very low intensity, much less radiation than taking a flight or having a banana or anything else. But what happens is this beam of EM radiation flashes onto the Earth, and then radio astronomers or X-ray astronomers can detect it, okay? That's what happens when it points towards us. But because it's rotating, it's not always pointing towards us. Sometimes it's pointing the other way, okay? We're occasionally in the path, but only when it's facing in our direction, okay? Now, as it rotates, it blinks, okay? Sometimes it's facing us, sometimes it's not facing us, and this leads to this pulse-like behavior that was first observed by Jocelyn Bell. This is why we call them pulsars. We see these pulses of electromagnetic radiation in these dips here, which in the case of the pulsar that Jocelyn Bell discovered were exactly 1.3 or about 1 1/3 seconds apart, okay? That's why they pulse. It's not that the beam of radiation is turning on and off, like a pulsing headlight if you flash your lights at someone. It's just that the direction, like a lighthouse, is spinning around. So sometimes it's shining right on us, and sometimes it's shining away from us. That's why we see these pulses, okay? So that is all I had to talk about. I thought now we could take some questions. So you can ask questions about pulsars, but I'm happy to take a couple more general questions as well about physics and so on. So does anyone have any, first of all? I'll come back to you afterwards, Henry. I'll just see if anyone else has one, okay? Does anyone have a question? No? Oh, you're much less talkative than I expected. Oh, yeah, you have one. Yeah, brilliant. Ah, that's a really good question. Yeah, I wasn't very clear about that, was I? So they're the same thing, really. It's just the pulsar is very quick spinning. So every pulsar is a neutron star. It's a spinning neutron star. But not every neutron star is a pulsar, if that makes sense, because some of them are not spinning super quick, so they don't have these beams of radiation coming out of the poles, so they don't make that sort of pulsing light as they spin around and shine on us. But yeah, that's a great question. Every pulsar is a neutron star, but some neutron stars are not pulsars. Okay? Does that make sense? Yeah? Do you have a question?
Yeah. Is the fact that light is an electromagnetic wave, does that tie into how solar power works?
Yeah, so there's a whole theory of how light and matter interact. So this is the theory. The technical name is called quantum electrodynamics. It's the theory of how light and matter interact. And photocells in a solar panel work by taking the electromagnetic energy from light and converting it into electrical energy by exciting the electrons within these cells and making a voltage. Okay? Yeah. Yeah, at the back. Yeah.
How does the pulses travel to Earth if the pulsars are really far away from Earth?
Yeah, that's a great question. So, if you think about like a water wave, water waves need to have water to travel. Okay, when a water wave reaches the beach, it stops waving because there's no more water to travel through. Now, electromagnetic waves like light are very special because they don't need anything to travel through. They can travel through completely empty space and will just keep going and going and going forever. So, if you shine a torch out into empty space, the light that comes out of your torch will keep going and keep going until it hits something. But, it could travel for millions and millions and millions and millions of miles. So the light that comes from the pulsars, the X-ray light, it only ends when it hits something. Okay? It can go on forever and ever through space. Yeah? Henry, did you have a question?
Yeah, so about the pulsars. So what would happen if they hit the sun, as the sun is a completely different thing to our planets, as it's got already loads of radiation in it? What would happen?
Ooh, I mean, if it hit the sun, if it collided with the sun, it would be pretty bad, because the pulsar has a weight that's larger than the sun itself. It's more like the sun would hit it. The sun would be pulled towards it, so it would probably rip the sun apart. But in the process, it might do something called a type 1 supernova. Okay, so a type 1 supernova, these usually happen with white dwarf stars, not pulsars. This is where a larger star gets sort of some of its material ripped off of it by a small dead star, like a neutron star or a white dwarf. And when it rips some of this material off, it squashes it down very tight on its surface, and it causes a big burst of nuclear fusion. So we have a sudden flash of energy and a sudden flash of heat and light and things thrown off. Okay? But it actually depends on how heavy the neutron star was compared to the upper limit for how big a neutron star can be. So neutron stars can't get too large. There's a mass limit on how big they can be, beyond which they actually collapse down into a black hole. So if this neutron star was very near to what's called, again, some jargon, is called the Tolman-Oppenheimer-Volkoff limit, which is a great one to remember for dinner parties, it would actually collapse into a black hole. So it depends how big it was. It would either have a type 1 supernova and flash suddenly, or it would collapse to a black hole. It's a great question. Yeah?
Neutron stars have, as you said, very strong electromagnetic field.
Yeah.
Do they have an iron core?
No, not an iron core. So this is the thing, because
How is that generated?
Exactly. So yeah, so there are different kinds of magnetism. So the magnetism of a solid piece of iron is ferromagnetism. But of course there's paramagnetism and diamagnetism. And then there are more sort of exotic kinds that are arising from the exotic structures within the neutron star. These kind of superfluidic neutron matter. The exact origin of the magnetic field is not known. I mean, neutrons themselves have a magnetic dipole. They are themselves little magnets. And if they all lined up, they would create a magnetic field. But the magnetic field of a neutron star, like I say, it's about 1 trillion times stronger than that of the Earth. So just including the magnetic fields of the neutrons being lined up doesn't give us enough of a magnetic field. So the sheer size of it is the mystery. It makes sense that there's a little bit of one, but the fact that it's about 1 billion times bigger than we would think it should be. Yeah, it's a great question. Yeah.
What are black holes made of?
Ooh, so they're not really made of anything. They come from stars, but actually they don't have a physical surface. They're not like a solid surface. They have at the center what's called a singularity. So this is like a point of infinite density, where all of the mass of the star has been collapsed down to something smaller than an atom. And then surrounding them, shielding this exotic, mysterious singularity, there's the horizon of the black hole. This is the part that you can't pass beyond. If you go within the horizon, you can never get out. But it's not a solid surface. If you were falling into a black hole, you could happily fall into one and pass through the horizon without feeling very much. But for someone looking on outside, they would see something quite different as you passed through it. So if you want to know more about that, though, I am giving some more talks in May, and one of these is on black holes on the 25th of May. I'm also talking about particle physics on the 11th, and then we're going to talk about time travel on the 18th. Okay? I just thought I'd flash those up. And additionally, if you want to see the notes from my talk today, these are posted on my website. If you go onto my website, just linked there, and you go onto lecture notes and recording, you can see the slides I've used. So I think we're just about out of time. We can maybe fit in just 1 or 2 very quick questions just in the last minute. Yeah.
You say that the pulse travels until it hits something.
Yeah.
Does it mean the ones we get are the ones that travel through the universe and didn't hit anything until it reached Earth?
Yeah. The universe is very empty. The universe is very empty.
Oh, yeah, I know. That's why we can't see anything with the telescope at night. It's like really odd.
That might be the light pollution.
No,
Yeah.
it's like if you move like a micron,
Then there's nothing there. Yeah,
whatever.
exactly.
Micron for me probably means 100 light
Billions.
years.
Yeah. Exactly. Brilliant. Henry, yeah, last one.
So about a singularity in a black hole.
Mm-hmm.
The black hole is like supermassive black hole.
Mm.
Does that mean the singularity would be significantly smaller or significantly bigger?
It's a hard question because it's basically no size in any case. It doesn't have a size. It's a literal point. You make a dot on the page with your pencil. That's still billions and billions of times bigger than I'm talking about. It's a literal point. But ultimately, the singularity is completely mysterious because it's also the point where our laws of physics break down, and we can't do any equations or do any maths with the singularity of a black hole. People say it's like where God decided to divide by 0. The equations just don't work. So completely mysterious.
Have we actually seen a black hole?
We have seen them, yeah. So we discovered them first, by the radiation they emit, gravitational radiation, ripples in space when they collide. But we have since seen them actually with an optical telescope. We can see what they look like. It's very difficult. So
Can you actually see the singularity?
no.
Or
So
just the horizon around?
the singularity is always shrouded in the horizon, but you can't even see the horizon because the horizon is black and space is black. So it's very hard to see them. But what you see is the glowing, in-spiraling material that falls in.
You see the stuff around
Exactly.
that is being pulled inside that singularity.
That's right. That's exactly
So
it.
we don't actually know what the singularity is.
No, completely mysterious. Yeah. Okay. Thank you very much. And yeah, please do come to these. Thank you.